And in this last part of the lecture, we want to look at the Earth's moon, which is particularly special, and then a few other things beyond that. But we'll mainly be looking at the moon in this lecture. Now, more is known about the moon than any other celestial body. We've actually physically gone there. We've put people on the surface of the moon. We've brought samples back to analyze. Um, it's We also know its size, its composition, its density, all kinds of things about it. We know its diameter is about a quarter that of the Earth. We also know it has no atmosphere, for the same reason that Mercury has no atmosphere. It doesn't have enough gravity to hold one in place. Because it doesn't have an atmosphere, there's no wind, there's no rain, there's no erosion. And so, for example, the astronauts set foot on the moon back in the 1970s. Their footprints are still there because there's no wind, there's nothing to get them to go away. Here is a picture of Buzz Aldrin on the surface of the moon. He is one of the three Apollo 11 astronauts. He and Neil Armstrong were the first two humans to ever set foot on the surface of the moon. Here we see a picture of the moon, and here's an inset that's been blown up, and then here's another inset that's been blown up further. And even with a good telescope on Earth, you can see this kind of structure. You can see the craters and the sort of mountain ranges. It's really kind of pretty. It's, sort of I've heard it referred to as beautiful desolation. The moon is kind of a lonely place, but it's certainly striking in its appearance. Now, one of the things that's really interesting about the moon is that it is tidally locked to the Earth. That's a fancy phrase, and I'll explain what it is and then, really just what it means, which is the important thing you need to know. Basically, what it is, it's a synchronization of the moon's rotation rate about its own axis. So the moon, like the Earth is spinning around its axis, the moon is spinning around its own axis as well. And then the moon is also at the same time revolving around the Earth. And those two motions, those two rotations are synchronized so that it takes the same amount of time for the moon to make one complete turn about its own axis as it takes to make one complete revolution around the Earth. And so consider you've got a person here, he's on the surface of the moon directly above the Earth, and as the moon moves around the Earth, it's moved from here to here. Now, if the moon were not rotating, this guy would be pointing up there somewhere, would not be pointing at the Earth. But because as the moon has rotated down and it's spun about its own axis this certain amount, this person is still facing the Earth. And all through the orbit of the moon, that synchronization occurs. The long story made short is this. When we look up at the moon, no matter where it is in the night sky, we always see the same face of the moon. We always see this side of the moon. We never see the back side. And that's kind of interesting. If you look at the moon, notice it always looks the same. Even though it's spinning about its own axis, because it's also spinning about the Earth, they line up in such a way that the Earth always sees the same face of the moon. So here's a picture most people have never seen. And this may be the coolest picture in this entire course that I've given you. This is the back side of the moon. The side of the moon nobody gets to see, or almost nobody gets to see. We've actually sent ships around the moon and that have taken pictures of, the entire surface of the moon. And so this is the back side of the moon. Pretty darn cool, right? Now, for a long time, people asked the question, how did the moon get there? And there were a lot of competing theories. But we now believe, and there's very strong evidence for the idea, that early in the Earth's history, it was struck by another planet, a planet somewhere between the size of Mercury and Mars. A small planet struck the Earth in a glancing blow, and that small planet was completely obliterated, and it smashed the Earth good too. And basically, what happened was the Earth, so much energy was released, the Earth just liquefied. It became this big ball of liquid magma, and the debris of that other planet that was just shattered in the collision, it gravitationally attracted and coalesced, and it eventually came together and formed our moon. And so our moon actually comes from another planet that smashed into the Earth billions of years ago. And what's really startling is this whole process of this planet striking into the Earth and basically being blown up by the collision, and all that dust and debris coalescing and reforming, that took about a year. So that's a pretty cataclysmic event in the Earth's history, but that's how we got our moon. Now, the other thing that we see about the moon that's kind of interesting is that the moon has phases, and you guys know that the moon sometimes looks like a crescent, or maybe there's half of a moon, or a not quite full moon, and then there's the full moon, and then it goes back the other way. The reason that the moon has these different phases has to do with where the moon is relative to you and relative to the sun. And so I'm not going to go into every possible example, but I think, contrasting the new moon with the full moon is a pretty good example of why we see different phases. So basically, here's the idea. Imagine that you are standing on the Earth and it's midnight, and when you look up, the moon is directly over your head, and the sunlight, because it's midnight here, the sunlight's coming from the opposite direction, and so some of that light passes around the Earth and strikes the surface of the moon and gets reflected back. And so you actually see the full surface of the moon. Now, if the moon were over here, you would not see the entire half of the moon that's being illuminated by the sunlight. You'd only see a sliver. And so that's why we see some different phases. Now, if you're standing here at midnight and the moon happens to be on the opposite side of the Earth, you're never going to see the moon. So that's why sometimes there's no moon in the night sky at all. The moon is actually on the opposite side of the Earth, so you can't see it. That's called a new moon, by the way. When you look up and the sky is just dark and there's no moon, that's a new moon. And then what happens is you get a waxing crescent, a quarter moon, a waxing gibbons, and then a full moon. The waxing means the sliver of light is getting bigger and bigger and bigger. So from the new moon, where there's no moon visible in the sky, all the way to the full moon, where the moon is completely illuminated. Then, as the moon moves to another position, you get the waning gibbons, the last quarter, the waning crescent, and then the new moon. That means the amount of light is getting less and less as the moon moves along its orbit. So waxing means you're getting more light day to day. Waning means you're getting less light day to day. The next thing I want to talk about is an eclipse. Now, there's two different kinds of eclipse. There's what's called a solar eclipse and a lunar eclipse. And so the solar eclipse is when the moon is in between the sun and the earth. And so basically the sunlight is blocked by the moon and the shadow of the moon falls on the earth. This is called a solar eclipse. Now, it's kind of funny, as there's a coincidence. The sunlight coming from, if you're on the earth right here and you're looking at the sunlight coming in from the top of the sun and the bottom of the sun, it makes a cone going into your eye, and that cone has an angle. The moon is just the right size and just the right distance from the earth that it would line up to completely block the sunlight. If the moon were further from the earth, so that the moon was like over here somewhere, some of that sunlight would get through and you would never have a complete eclipse like we can have today. But because of where the moon is and just how big it is, that it actually matches almost perfectly. And that gives rise to a solar eclipse. Now, a lunar eclipse occurs when the Earth is between the moon and the sun. So the Earth's shadow falls on the moon. Now, if you're standing right here and you're looking up, you might think that the sunlight would be completely blocked. But actually, some of that sunlight gets past the Earth, and some of it actually passes through the atmosphere and gets refracted like we talked about. And remember how we said when the light goes on a long path through the atmosphere, the blue gets scattered out and the red light is what remains? Well, that happens as the light passes through the Earth's atmosphere and illuminates the moon. During a lunar eclipse, the light that ends up on the moon is the red light. And so if you've ever looked up at the night sky and seen the moon, and it's this orange or red-orange color, that's what's happening. You're having a lunar eclipse where the Earth is blocking the sunlight and preventing the moon from being fully illuminated, and that creates a lunar eclipse. But it is still illuminated by that red light bending around the atmosphere. And so you can see here's a picture showing the moon during a lunar eclipse, and you can see it really is reddish, and so that's pretty cool. And that's because the light falling on it and being reflected back from it is the red light that has been left over as all the blue light got scattered out by the Earth's atmosphere. Now, I mentioned previously there is a belt of asteroids that exists between Mars and Jupiter. And what are asteroids? Asteroids are small rocky bodies that orbit the sun. As I said, most are located between Mars and Jupiter, but occasionally some of them get knocked out of their orbits by collisions or whatever, and they end up crossing the Earth's path and crashing into the Earth. Another thing that exists in the solar system are comets. Now, comets are different from asteroids. They have different chemical compositions. Comets are mainly made out of water and methane and ice. They're basically dirty snowballs. Most of them are located in that Kuiper belt and something called the Oort cloud, which is another thing. It's like the Kuiper belt, but it's out even further. And comets have very highly elliptical paths, very elongated paths, and the tails of comets are swept outward from the sun by the solar wind. So basically what happens when a comet gets close enough to the sun, the solar wind causes some of it to melt, so the comet is basically this big ball of snow, dirty snow, and the solar wind basically heats it up, and as it's going towards the sun, the solar wind causes the comet to trail off. And so that is why comets have that long tail like you've seen. So this is showing a little bit more about comets. So in this slide you can see a few prominent features. So the Earth's orbit is technically an ellipse, but it's practically a circle. And the comet's orbit is a much more elongated ellipse. And you can see it's got a much longer path. So out here far from the sun, a comet's just basically this dirty snowball. But as it goes closer to the sun, it gets warmed up and some of it basically starts to melt and turn into, kind of something like steam. And then as it goes, it gets closer to the sun, more and more of it. Now you can see the tail is directly away from the sun at every point in its path because the sunlight is, accompanied by that solar wind that is, causing it to push away. And so you can see the tail. Now, when the Earth's orbit is close to the comet, we can actually see the comet from Earth. When the comet's out there, you can't really see it except with a telescope. Maybe not even then if it's far enough away. But when it's close to the Earth's orbit, sometimes we are able to see these comets. Now, there are some other terms that people mix up a lot, and so I just wanted to go through them really quickly in case you hear some of these terms, you'll know what they mean. Meteoroids are relatively small, that means sand grain to boulder size, pieces of debris that are chipped off of asteroids or comets. So basically, a comet or an asteroid collides with something else and a piece of it breaks off, and sometimes that happens and those pieces make their way to the Earth, and those are called meteoroids. Now, a meteor is a meteoroid that actually strikes the Earth's atmosphere. Sometimes it's called a shooting star or a falling star. Of course, it's not a star at all. It's a meteor. And again, so a meteoroid is just basically a chunk of an asteroid that's been knocked off and it's just floating around in space. A meteor is what it becomes when it enters the Earth's atmosphere. Now, if it actually makes it to the surface of the Earth, most meteors, when they impact the Earth's atmosphere, the friction that is caused by them passing through the Earth's atmosphere, it heats them up so much that they vaporize. So they don't ever make it to the surface. But if it's big enough to actually hit the surface, then it's called a meteorite. And so a meteoroid that makes it to the atmosphere is called a meteor, and one that actually gets through the atmosphere and hits the ground is called a meteorite. And that's that for our lecture on Chapter 26.